Welcome back to our third installment of astronomy. And the realm of geoscience, astronomy is just one discipline, but a very important discipline that we need to look at. And there's so much we can learn about our own planet by investigating the cosmos. That's been a common theme through each of our installments. So thus far, we took a look at the universe. So we started big. We looked at how old our universe is, the process of how it expanded, the different stages of its formation, and about how long each of those steps took. We investigated how galaxies are made. And then we looked at the various different types of galaxies. Then we investigated the stars and how stars grow, evolve over time, and ultimately explode into supernovas. And the supernovas are so important to the formation of brand new baby stars. And in the realm of the age of our universe, our sun is a baby star. It's new. It's not been around very long. So we're looking at somewhere around 4.6 billion years ago that our sun became a star. And how did our planets get there? What else is in our solar system? Scientists have been looking to the cosmos for as long as humans have been around to figure out some of those very questions. And truly, in the last 50 to 100 years, just an enormous amount of technology and advances in how we do science has helped us get a better grasp of this. And we are nowhere near done. So as a scientist, I have to own that and tell you that in 10 years, 20 years, our understanding may be completely different. And you'll look at a couple of examples of that today as we look at the exploration section of this installment of astronomy. So the International Astronomical Union, known as the IAU, they're an important group. They are pretty much the regulatory agency, for better lack of words, who determine what bodies out in the cosmos qualify as different specific types of bodies, which we'll go through in just a second. I can remember as a child growing up with 9 planets, but in 2006, we went down to 8 planets. And we'll talk about why. Because the IAU made a decision, and rightfully so, based on a definition they came up with. And you might wonder, why did they come up with all these different terms for celestial bodies? And there's a definition needed to qualify for each one. One thing is for sure, there are 3 major parts to our solar system. There's the inner solar system that contains the terrestrial planets, and we'll look at those in a sec. Then there's the outer solar system. Those contain the gas and ice giants known as the Jovian planets, and then the Kuiper belt and the Oort cloud. So way in the outside edges of our solar system, beyond our last planet, is the Kuiper belt, and then kind of the exterior shell that kind of holds all that in is the Oort cloud. So we're going to be looking at these different topics and more. Let's first talk about an astronomical unit, or an AU. These are important because in space, distance is so vast that we need some kind of a reference for humans to relate to. So we describe distances in space based on astronomical units rather than just kilometers. So, for example, 1 astronomical unit is measured from our sun to planet Earth. That is the definition of an AU, or an astronomical unit. How long is that? Right around 93 million miles. So that kind of makes things more manageable when we're talking about space and we're talking about how far, even within our own solar system, planets are spaced from the sun, because there is a pattern, and the pattern is really compelling when you start looking at how far away the gas and ice giants are away from the sun and how far they're spaced from one another. So let's kind of think about Jupiter, which is our largest planet in the solar system, and it's 5.2 astronomical units away from Earth. What does that mean? In terms of not just a distance, it means that it takes 43 minutes for light to shine from the sun and actually reach the surface of Jupiter. That's how big a distance of time that really is. To Earth, that same light only takes us 8.3 minutes. So it's big when we're talking about astronomical units. Planets must meet 3 designated criteria according to the IAU. And these definitions are kind of what kicked out one of our outermost planets in 2006 and demoted it to a dwarf planet. So let's take a look at the 3 different criteria. First, it must be in orbit around a star. In our solar system, that would be our sun. But I do want to be clear, it could be in another solar system. Okay, so for testing purposes, it's not just our sun, it's a star, a sun. Number 2, it must have a sufficient mass for its self-gravity to overcome rigid body forces. So it must have basically a round shape. If it doesn't have that round shape, it doesn't qualify as a planet. It qualifies as something else. The third criteria, important criteria, it must clear the neighborhood around its orbit. In other words, it actually makes a rotation around its star, not just around another feature that's different from a star. So it clears the neighborhood. If it doesn't do that, it can't qualify as a planet. So the IAU set very specific criteria for dwarf planets, and dwarf planets changed the designation of a number of important celestial bodies in our solar system, 5 of which are shown here. Probably the most famous is Pluto, because Pluto used to be considered a planet until 2006. The IAU demoted it to a dwarf planet status. And here's why. So there are 4 criteria for dwarf planets. The first 2 are similar to planets. So they orbit around a star, or in our case, in our solar system, the sun. Number 2, they have a nearly round shape because they basically have enough mass to overcome the gravity issues, and they can have that round shape. Number 3, though, big change. This body does not and cannot clear its neighborhood in its orbit. That's why Pluto got changed from a planet to a dwarf planet. And number 4, this is one that people don't often think about. It does not meet the definition of a satellite. So if you don't meet any of these criteria on a definition set by the IAU, you have to be a different type of celestial body. So planets have 3 basic criteria. Dwarf planets have 4. Let's investigate the next one. Satellites. We're going, oh, I know what a satellite is. Of course you do. You know what a man-made satellite is, but there are also other satellites in outer space. So if you just did an internet search, you would see that certain groups might qualify anything that's out in outer space as a satellite, but that's not what the IAU said. So anything that orbits, including man-made devices, can qualify as a satellite, but they must meet these definitions to formally be recognized by the IAU as a satellite. They do not have sufficient mass to self-gravitate into a spherical shape, unlike our planets and dwarf planets. And number 2, it has a primary orbit around a planet, a dwarf planet, or a small solar system body, which is the 4th type of celestial body. So it's not just what we put in outer space. They can be other things that are not big enough to be a dwarf planet, not qualify as the 4th type of celestial body or a planet. Small solar system bodies are the 4th type of systems recognized by the IAU as a body in outer space, a celestial body. So they define all other objects except for satellites orbiting the sun as small solar system bodies. And examples of these can be things like asteroids, meteoroids, comets, moons, and interplanetary dust. So they don't meet the definition of a dwarf planet. They don't meet the definition of a planet. They don't meet the definition of a satellite. There's something else. There are lots of small solar system bodies out there, certainly more than there are dwarf planets and more planets. So let's keep looking and seeing what we have in our solar system. When we think of the inner solar system, I want you to think of Mercury, Venus, Earth, and Mars. These are planets that are predominantly made of rock material. So they have, in most cases, an inner core made of some type of dense material, and then they have different layers. So you get to the outer crust, and those crustal pieces are made of rock as opposed to ice and gas material like we'd see in the gas and ice giants out in the outer solar system. These planets also have faster rotations around the sun because they do not have as far to travel in their elliptical orbits, which makes sense. And these planets do not have interplanetary rings like you might see the faint ones on Jupiter and Saturn, some of the other planets that we have out in the outer solar system. These planets got hammered in the early existence of the solar system. They were not alone. Some of the other ice giants and gas giants were also bombarded, but the inner planets got hit the hardest. And so subsequently, they are full of impact craters, some of them more than others. So we will take a look at those as we go through the planets. Let's start with the one closest proximity to the sun as Mercury. You would think Mercury would be the hottest because it's the closest. It is not. Actually, Venus wins that prize, and it's because of its greenhouse runaway situation with being so hot with the greenhouse gas, the emissions coming primarily from volcanism. So we know that Mercury is just covered basically with craters from being bombarded during the period of time in the early existence of the solar system, which makes very good sense because Mercury would have received the first blast of material coming from the sun as it was the first planet in line. So it's definitely covered with lots of craters, but it's not alone in this phenomenon. It has the fastest rotation of all the planets, and it orbits the sun every 88 days. It has the shortest elliptical orbit, which is the reason why it's the fastest. Venus is number 2 away from the sun, so Mercury, Venus. It's the 6th largest planet in our solar system. It's also ranked as the number 1 hottest because it has such a thick carbon dioxide rich atmosphere, caused by primarily from greenhouse gas emissions that have been emitted as outgassing from volcanism. We know that it's volcanically active, and we now have proof of that. So that's an important thing to know because that does contribute to the big picture of Venus's issues. It has a day longer than its year, so it's really interesting that it has no recognizable seasons. To be honest, Venus, we have a lot to study because we have to get through its thick atmosphere and deal with its immense heat to be able to study it. We can study Venus through other means of remote sensing, satellite orbits. One day, we'll probably be able to get something down there, but the surface of Venus, this is important, is hot enough to melt lead. Wow, hot enough to melt lead. Crazy, right? So that's super hot where Venus is concerned. Moving to the third slot in the solar system that belongs to planet Earth. This is the only place that scientists know thus far that inhabits living organisms that we know to date. That could change, but right now in our solar system, we're kind of considered a Goldilocks planet, which are those planets that exist in just the right proximity from their stars, that they could have not too much heat, but not too much cold, and potentially have all the right ingredients for biological life to survive. We have an atmosphere conducive to biological life because it's rich in oxygen and hydrogen. The oxygen is a key component of that. We also are considered a dynamo planet. What does that mean? What a fun term, right? Dynamo. It means we have a solid core and a liquid outer core that spins around it. When this happens, a little geomagic occurs and we get a geomagnetic field. Without that geomagnetic field, our atmosphere would blow away. So that subsequently, we would not have a protection from the ultraviolet radiation of the sun. We would be impacted by solar winds. Let's just say Earth would not be inhabitable. So to be a Goldilocks planet, you kind of have to have all those criteria, and Earth certainly qualifies as the premier candidate of Goldilocks status. Mars, a planet that's dear to my heart. I spent some time at the Mars Desert Research Station, known as MDRS, in Hanksville, Utah, to live in simulation like we were on Mars. So a group of professors here at the college decided to test this out and be on a mission. So we had a mission commander. We each had a role that we assumed just like they would if they were traveling in space. If you saw the movie The Martian, you saw a little bit of how that worked. And you had to wear spacesuits outside, even though we were on planet Earth. We had to treat like every time we stepped out of the hab, which is the habitat, that we would be on the surface of Mars. And out there in Hanksville, Utah, it doesn't look too different from what we've seen from some of the rover images of Mars. So Mars is the fourth planet in the lineup. There's Mercury, Venus, Earth, Mars. So it's pretty much the last planet in the inner solar system before you reach the big asteroid belt that separates Mars from the outer part of the solar system. It's our seventh largest planet, and its surface is very challenging. It is dry, rocky, and very cold. So robotic orbiters found evidence on Mars, which was pretty incredible, that it once was much wetter, warmer, and conducive to forming flowing water conditions, because we have evidence of ancient fluvial or river systems. There's evidence of ancient volcanism on Mars. Mars right now does not produce those, so it's not plate tectonic active system like Earth, and at least not in the same stage. But this is a really important thing. If there was a place that we could inhabit besides Earth, this would probably be the candidate. And that's why so many of the studies and lots of money is being poured into colonization of other planets as to looking at how are we going to deal with our climate issues that we have on our own planet and population growth and sustain human population without enough resources, space, and food, and so forth. So Mars is being looked at as a potential candidate, and there's several of these research stations across the globe that I discussed. There's one in the Arctic as well, and that's a very tough situation to endure. I've also, one of our commander actually had been to that one as well. When we think of the outer solar system, that's basically everything from the meteorite belt outwards. So I kind of look at the meteor belt right in the middle of in between the inner and outer planets as the boundary between the two. And the outer solar system involves Jupiter all the way out to where our dwarf planets are in the Kuiper belt. So these planets are predominantly considered gas and ice giants. They're all just huge. That's an understatement. Compared to what the size of planets are in the inner solar system, we are just little bitty compared to them. And the spacing of these exponentially just gets larger and larger away from the sun. So there are two gas giants in the outer solar system. Those are Jupiter and Saturn. And then there's two ice giants, which are Uranus, also known as Uranus, and Neptune. Beyond Neptune, we have where our dwarf planets hang out called the Kuiper belt. And beyond that, which is the outer rim of the solar system, that is the Oort cloud. So most of our satellites that I talked about that are not man-made and small solar system bodies exist in the Kuiper belt, with the exception of the massive amount of small solar system bodies that exist in the meteorite belt between the outer and inner solar systems. Another important description to outer solar system versus inner are the terms terrestrial versus Jovian. Terrestrial basically refers to the rocky material that makes up the planets of the inner solar system, and Jovian refers to the gas and the ice that makes up the big dogs of the solar system, the very large bodies and planets. Let's start with Jupiter. This is the fifth planet in proximity to the sun. Remember, there is that dividing line between the inner and outer solar system, which is the meteorite belt. Very important part of our solar system. It is by far the largest planet in our solar system, and it has 2 times more mass than all the other 7 planets combined. That's how huge it really is. So where does the remarkable striping come from and coloration of Jupiter? It is directly correlated to its atmosphere. The bands and stripes that you see in swirls are made as an atmosphere that is rich in hydrogen and helium, so not in oxygen like we have. And that is what a majority of the planet is made of. This is atmospheric types of gases. So it's completely different, and it's the way it is composed and made and layered as a terrestrial planet would be. It is way too harsh for anything that's biological to survive that scientists think at this time could be on the planet itself, but there's at least a moon or 2 that could be a candidate for life to thrive. So the big red storm, the big red giant spot that it has is like a giant hurricane storm that's on steroids. It's really phenomenal. And it's been doing its thing for centuries. It doesn't show any signs of dissipation, but it does have a morphology change, and we can actually see storm systems from outer space now with the telescope capabilities that we have. So it's just phenomenal what we have and what we know about Jupiter now, with it being such a massive planet, an important planet to our solar system. Jupiter has a lot of moons. There are 95 currently recognized moons. That number could go up from the time you watch this video if the IAU classifies another moon or finds one that we didn't know. It also has a very faint ring or set of planetary rings like Saturn. They're just not nearly as bright as what we see in Saturn. It does not spin at an angle like our planet does. In fact, it's more straight upright, which allows for it to have not very good seasons. In fact, it doesn't have extreme seasons at all. In addition, the great red spot, that big storm I was talking about, continues to operate and continues to do its thing over these hundreds of years, and likely for thousands more if the right conditions prevail. So Jupiter actually has the shortest day in the solar system, but it takes 12 Earth years to rotate around the sun. So there's a difference between the length of day and the orbit cycle of these big planets versus the inner planets. So if you think about 12 Earth years, well, that's 4,333 days. You'd be on Jupiter a while before you made a full calendar year around the sun. All right, we're going to look at some of Jupiter's famous moons. Ganymede, what a great name. Like, I could name my next pet Ganymede. I love this name. It's the largest of Jupiter's moons, and it's the largest moon in our solar system. I think that's an important fact. It's also important because it has a magnetic field. That means it's got to have some kind of inner core, that relationship like Earth does for a geomagnetic field. So just like Earth, when solar wind comes through its area, you can get auroras, just like we have Aurora Borealis. They have the same kinds of things in their polar regions in Ganymede. There is really significant scientific evidence that scientists theorize that there's a very big underground saltwater ocean on this particular moon. That's interesting. And you can see where I might be going with that. So if that is the case, and we have a saltwater ocean, we have a magnetic field, we're a long way from the sun, so that is a limiting factor. But certain types of biological life might prevail there. We know Ganymede is rich with impact craters, so it's another one of those examples of structures in outer space, not just in the inner solar system, but in the outer solar system, that have been bombarded. And it has dark and bright terrain, which is important because we have learned that the terrain is different on Ganymede. The moon's surface itself is coated in a layer of ice, which kind of caps the whole thing in place. So Ganymede, again, the biggest moon of Jupiter, the biggest moon in the solar system, has that geomagnetic field, has the high probability of an underground saltwater ocean. Callisto is the second largest of Jupiter's moons and the third largest moon in our solar system. And Callisto is really a beautiful moon. It has bright spots that are believed to be ice, with the darker regions that are thought to be where ice has eroded away. So we do think, though, this is an important thing to know about this particular moon. Scientists theorize, based on evidence from remote sensing, from satellites that we'd put in outer space, that there could be an ocean beneath the surface, deeper beneath the surface, that interacts with rock, producing a habitat conducive to potential biological life. So this would be a place that we might look for that to occur. So Io is the third largest of Jupiter's moon, and I love Io, and here's why. It is an active volcanic wonderland. It's slightly larger than our moon, but about the quarter the size of Earth. But it's really special in terms of the fact that it's the most volcanically active place in our solar system. That includes with planets. Between Venus and Earth, that's a pretty important, compelling, active place to be. There are hundreds of active volcanoes that erupt lava, and from outer space, we can actually see this now with remote sensing, telescopes, all the technology we have. And these lava eruptions are just staggering. They can shoot up lava dozens of kilometers high. That's so different than what we see on planet Earth. So just as a geologist, that makes me marvel at the chemistry and the heat that's being produced that can make the necessary magmatic material that Io produces. The moon is caught in a gravity tug-of-war, basically, between Jupiter and its neighboring moons of Europa and Ganymede. So keep in mind that as the third largest moon, it's one of the really spectacular places where some really cool volcanism is occurring in our solar system. Europa is it's like the fourth largest of Jupiter's moons, but I like Europa. It's really special. It's made up of silicate rock, like much of a crust of planet Earth, and it has a water ice related coating to it around the surface. And scientists believe it has an iron nickel core like Earth, so there's a lot of similarities here. It has a thin atmosphere with very important constituent. It has a composition rich in oxygen. Wow, that makes it a candidate for something important. We could potentially have the formation of biological life there if other ingredients are present. Scientists believe beneath its icy surface that there is a saltwater ocean twice as big as all the salt water that's on planet Earth, making it an exceptionally interesting moon to study. So moving on into Saturn, so we had Mercury, Venus, Earth, Mars, Jupiter, Saturn. So we're at planet 6. 2 more to go. Saturn is well known for its planetary rings, and it has dozens of moons and some really cool features within the rings that we'll look at, called shepherd moons. It has the second shortest day in the solar system, 10.7 hours, and takes about 29.4 Earth years. Long time, longer than Jupiter, to make a rotation around the sun. It does have seasons, much like Earth, because its axis is similar, a little bit, not quite as tilted as ours, but close to it. So it definitely has seasonal weather, and that's an important thing. So let's take a look at its rings. What are they? You know, as a young child, I used to think, wouldn't it be cool to go sit on these rings on Saturn? There's some places that might be possible if you had the right gear, obviously, knowing what I know now as a scientist. But I'd like you to think about what the rings are composed of. They're made up of pieces of broken up comets, asteroids, shattered moons, lots of rocky material, things that you might call satellites or small solar system bodies, right? So that's what you got all in these rings. The size of ring material really varies. So some of the ring material is little, just tiny, tiny grains, like small pebble size and even smaller than that, all the way up to mountain-sized rocks. So there's a huge variety of material that makes up these rings. The rings orbit Saturn at different speeds. They're not all consistent, so they're actually labeled. They're given a number or a letter, and I'll show you one of these in just a minute. So the letters are like F is a really important ring for Saturn. Let's look at Y. Shepherd moons are most notable in Saturn's F ring, F as in foxtrot. Shepherd moons are the following. They are natural satellites. Remember that term satellites I was talking about? That's what most of these features are. They don't meet the definition. They're not, certainly not a dwarf planet. They're certainly not don't meet the small solar system body definition, but they do meet the definition of a satellite. So these are natural satellites that clear a gap in a planetary ring material. And basically shepherd moons are just like shepherds of sheep. They kind of hold everything together and make sure their presence is important to making the stuff not disappear or float away from the rings. So scientists look and see how much material is being lost or gained in these planetary, interplanetary rings like Saturn's, and they're not consistent. So there is change in the rings. That's an important thing to know. So the other gas giants have these rings too, but they're just not noticeable in the same fashion that we see in Saturn. Let's look at Saturn's moons. Titan is by far its most famous moon, and it is also the largest of Saturn's moon. It is the only moon in our solar system with a substantial atmosphere. Others have thinner atmospheres, but this one has the goods, right? Titan is also the only other place besides Earth known to have liquids in the form of rivers, lakes, and seas on its surface itself. That could be an important factor. Its atmosphere is mostly nitrogen, and the surface pressure is about 50% higher than Earth's. I'm not saying that life would, or biological life could survive or is present there, but there's some ingredients that make it an interesting place to investigate for that reason. Its subsurface water could potentially be conducive for life, but what a harsh environment to live in when your pressure at the surface is 50% greater than what we have on planet Earth. Another famous of Saturn's moon is Phoebe. And Phoebe does not orbit closely to the plane of Saturn's equator, which is common for most moons. It rotates on its axis every 9 hours and completes a complete orbit around its host planet of Saturn every 18 Earth months. This is a very, very dark moon, has an irregular orbit, which makes it an interesting thing to study. Scientists think it might have been captured by Saturn as a celestial body by its gravitational pull. Another famous moon for Saturn is Iapetus, and Iapetus is special because it has an albedo, a reflectivity that's extremely high in its brightness, as you see right here. And this is thought to be covered predominantly with ice. Take a look at that impact crater right there. And then the darker sections like this are thought to be primarily rocky material. So scientists think about 3/4 of the moon is an ice concentration material and the rest is basically rock. Like our moon, it's tidally locked to Saturn. So only one face of it is seen on the planet. And I think that's kind of cool that there's another planetary set of moons that happens with. And there is a massive chain of mountains that is on the equatorial ridge. And these mountains are monster huge for a moon. They're 10 kilometers high. So that's pretty impressive. So a moon with mountains, pretty neat. All right, there are two ways to say this planet, Uranus and Uranus. Depending if you want to use the Latin pronunciation, Uranus would be more accurate. I like Uranus, I just do, but either is acceptable when you're talking about this planet. This is the 7th planet from the sun. It is considered an ice giant, and it is the 3rd largest planet in our solar system. It has what sometimes people call the twin, which is Neptune. This planet is loaded with interesting stuff. It's, as you could guess, very cold and an extremely windy planet. This would be somewhere where if we had ever got something like humans or a craft that we could land on the surface of Uranus, this would be a very, very tough place to keep things from blowing off or blowing around because of the strength of wind that they have. This is a cool planet in the fact that it has 24 moons and it does have faint rings. So much like Jupiter, its rings are not that impressive like Saturn's, but it does have rings. It rotates about at looks like a 90-degree angle, so it looks like it spins on its side. And that is another cool feature of Uranus. So I'd mentioned that Uranus was windy. We're talking, I wasn't underscoring that. It's like 900 kilometers that it can be that windy, but it's much higher than that in Neptune. So over 1,000 to about 1,500 kilometers of wind. The colors are also noticeably different between these sister planets. Uranus has more of a cyan color, where Neptune is just a stark blue color. And the blue color comes from its methane-rich atmosphere, which absorbs all the red and wavelengths, leaving the blues behind. So that's what's reflected back to space. When it is windy here, I just think of the challenges of putting anything in Uranus or Neptune that we can really study its surfaces. Another fact about Neptune that's scientifically significant is this was the first planet that we discovered using mathematical calculations. So the calculations suggested what's called, there's a set of laws that we used for planetary spacing, and Neptune had not been discovered yet or seen scientifically, but we knew it was there. And sure enough, when the technology reached that point, the calculations were correct, and sure enough, there was a planet known as Neptune. So let's revisit the planets. We had Mercury, Venus, Earth, and Mars as the inner planet. We have that boundary marker between them, which is the asteroid belt. That's where a majority of our small solar system bodies exist. And then we have the outer planets with Jupiter, Saturn, Uranus, and Neptune. So what exists beyond them? Okay, the dwarf planets. Now, not all dwarf planets exist in the Kuiper Belt, which we'll be talking about in a minute, but Pluto certainly does. There's a very important dwarf planet that used to be categorized as an asteroid that exists in the asteroid belt, but most of our dwarf planets exist out in the Kuiper Belt. And in 2006, poor Pluto got demoted as our tiny little, what we call the little planet. And lots of people protested over this, very upset about it. But quite frankly, it doesn't meet the definition that the IAU put. It doesn't clear its orbit. So it cannot be a planet by definition, but it certainly meets the definition of a dwarf planet. Pluto has valleys, plains, and even glaciers, and certainly evidence that it's been bombarded. It is out beyond our planetary reach in the Kuiper Belt, making it an interesting dwarf planet to study. Ceres was also another object in our solar system that was reclassified when the IAU made the definition of a dwarf planet. Ceres is the largest object in the asteroid belt between Mars and Jupiter, and by far was the largest asteroid for years until they classified it as a dwarf planet. It is the only dwarf planet that is located in the inner solar system, and I think that's an important fact about its position in all of this area. So I'm not saying this would happen, but just theoretically, if something the size of Ceres were to be escaped from the asteroid belt, this could have just ginormous implications for any planet if it were to collide with a planet. Now, Ceres was called an asteroid, and it makes up 25% of the asteroid belt, so that's a lot of mass. So when they took that designation and upped it to a dwarf planet, the mass of the asteroid belt diminished greatly. In comparison to Pluto, it's 14 times smaller, so Pluto is by far the largest of our dwarf planets. Eris is another famous dwarf planet. It's about the size of Pluto, but 3 times farther distance in the Kuiper Belt, so 68 astronomical units. That's a long way away from where we are. And it's about the 5th the size of Earth, but just another example of these features that we didn't even know existed until we had the right technology to look deeper into space, especially this far away. So, Pluto was just a fuzzy thing out in outer space for a long time. Then we got the Hubble telescope, and then when we got the Webb telescope operational, boy, the things we can see beyond in our solar system and beyond in a much clearer manner is remarkable. Makemake, isn't that an awesome name? Makemake. This is a dwarf planet located in the Kuiper Belt. So all the dwarf planets but one, which is Ceres, exist in the Kuiper Belt. This is one of those dwarf planets that deserves a little recognition because it's the important part of astronomical studies, because its discovery was one of the primary reasons that the IAU considered the definition of a planet. Up until then, Pluto was still a planet, and finding this one made them look at what is a dwarf planet. And that's how dwarf planets kind of came to be, and also why Pluto and these other structures, whether they were asteroids or they were considered a planet at that time, Pluto was the only planet that was demoted. The rest were promoted from usually asteroid or even not even discovered at the time. And that would certainly be the case for this one. That brings us to the Kuiper Belt. The Kuiper Belt is the outer reaches of our solar system, and it contains icy bodies, leftovers of the solar system far beyond the orbit of Neptune, but still considered part of our solar system. It's similar to the asteroid belt, but thought to be a region of leftovers from the solar system's earliest reaches and history. So if asteroids from out here, meteors, work their way through the solar system, so some of the original leftovers were to escape out of the Kuiper Belt, make their way all the way past all these incredibly huge gas and icy giants in the outer solar system, somehow miss everything in the asteroid belt in between Mars and Jupiter, got past Mars and made it to Earth. Wow, that means impressive, right? Didn't burn up in our atmosphere and landed on planet Earth. These might be some remarkable meteorites that we could have. Why is that? Because they likely have some of the oldest material of the solar system. So just to kind of put it into perspective of what you learned in the last 2 lessons for astronomy. the makings of our sun, the earliest days, we had a lot of stuff that got pushed away from the sun by solar wind as it was forming and once it got formed. And that's where that big bombardment period we were talking about happened. And so the lighter elements that make up the gas and ice giants, while some of the inner planets retain some of those gases, like some methane, hydrogen, helium, most of the majority of that blew outwards towards the outer solar system, and so did the lighter weight material. If that weren't the case, we would have a meteor belt right around where we exist, or even by Venus, and that's just not the case. So the tiniest stuff has been blown out over that period of time, and a lot of it has been sitting out in the Kuiper Belt, which quite frankly has been a mystery. As science has become more technologically advanced, our knowledge of the Kuiper Belt has exponentially grown. This is an area future NASA want to research because there's a lot that we can learn about this Kuiper Belt. But that's not the very edge of our solar system. The Oort cloud is. This is basically the giant spherical shell that surrounds the outer edges of our solar system, kind of, if you want to call it the coating of it, the system that holds all of the Kuiper Belt, all the stuff inside of it. It contains icy pieces of space debris ranging from small, tiny little pieces to literally mountain-sized rocks. And they believe, as scientists, that the Oort cloud may contain billions or even trillions of celestial bodies. But we don't know very much about it. We know it exists. We have some images of it, but there's a lot of research that could be done just within our own solar system if we can get satellites out there to study them. So moving past planets and dwarf planets, we're going to look at some of the other celestial bodies. Some of these would be what we'd call small solar system bodies, and asteroids are one of them. Majority of our asteroids, which we consider to be space rubble clutter, space rubble is a more scientific description, but they exist in our solar system, and a majority of them in the boundary marker between the inner and outer parts of the solar system, and that is the meteor belt or the asteroid belt that we've learned about. They also exist in the Kuiper Belt. So asteroids typically have irregular shapes. If they had that round shape, they would and could basically meet the definition of a dwarf planet, they would be called that. So there is a feature in this belt that we know of called Ceres that used to be one of these that got upgraded to a dwarf planet, but in most cases, a majority of this stuff does not. Like the Kuiper Belt, there's a lot of goods in the asteroid belt. And these rocky materials can give us a lot of clues about what the earliest chemical makeup of our solar system used to be in terms of the rocky material. And that's pretty much what exists in that boundary marker between Mars and Jupiter. Asteroids can range from being over 500 kilometers down to 10 meters across. So they range, they're they're variable. There's just no one size fits all. Interestingly, though, the total mass of all asteroids combined are less than the Earth's moon's mass as one thing. So sometimes we think of them being just massive, 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 but when you look at them as a whole, they don't have the same size and mass that we do with other planetary and moon structures. Vesta is the largest asteroid in the asteroid belt between Mars and Jupiter. It didn't used to be. When Ceres was still listed as an asteroid, when I went to college, Ceres was just that. It was an asteroid. There was no such thing as dwarf planets. But when Ceres got upgraded to dwarf planet, this guy took #1 seat as the largest asteroid, making it the second largest body in the asteroid belt. It consumes 9% of all of the mass. That's of the asteroid belt itself. So it's a pretty substantial asteroid. NASA's Dawn spacecraft circled this asteroid for about a year. In their research, they discovered that this particular asteroid is so significant scientifically because it was one of the first things formed in the early existence of the solar system. We're talking like in the first 1 to 2 million years as the sun was being born and these objects were being blown away from the sun. So that's how significant Vesta is. It appears to be the source of specific meteorites found on Earth. In other words, it is the same type of meteorite. And that's important to scientists because during the period of time when repositioning of the gas giants billions of years ago occurred, this destabilized the orbits of a lot of meteorites and asteroids, triggering a massive period of bombardment of asteroids throughout the type of meteorite that Vesta represents is important to scientists because we find them on Earth. In addition, we know that this type of meteorite represents a period of time when the gas giants were kind of being repositioned in outer space. And this happened billions of years ago, but when they did, it destabilized all of the orbits of the asteroids in that part of the solar system, causing a period of massive bombardment throughout the solar system, both in the inner and outer portions of the solar system. And we call this massive bombardment, it has a name, it is called the lunar cataclysm. So this particular event is so important. Another important asteroid is Eros. Eros also is a number, and I'll tell you, your asteroids have numbers. They've been numbered, and then they have a name. This was the first asteroid to ever be orbited by a spacecraft, making it scientifically and historically significant. And it's the first one that actually had one to land on its surface in 2001. That was the near Shoemaker. Shoemaker's a guy you learned about in the last lesson. During its spacecraft landing, gamma ray experiments were done. Why is this significant? It's the first time besides on planet Earth that has occurred. So this particular asteroid has it going in terms of being significant in advancement of us knowing what these things are made out of, because that's exactly what the experiments tell us. Itokawa is also another important asteroid. It is 25143 and its number. This is important because not only did a spacecraft land on it, it collected samples and sent them back to Earth. And as the name suggests, this is not an American name, so it was a different country that did it, but is such a remarkable leap forward in astronomical studies. So this occurred back in 2010. This particular meteorite is an ordinary chondrite, which you're fixing to learn about what the different types of meteorite materials are. And that's certainly the most common that we find on Earth. It's a type of stony meteorite. That brings us to the fancy terms of meteoroids, meteors, and meteorites. Which one is which? And what is an asteroid? So the asteroids are the things that we were just talking about. So meteoroids are all-inclusive term that includes those. They are small bodies moving in the solar systems, but meteors are meteoroids that enter Earth's atmosphere or in other planets. So it doesn't just have to be ours. And when they enter the atmosphere at high speed, they tend to burn up, which makes them look like a shooting star. So if you've ever seen a shooting star, a remarkable sight to hold in the sky, that is what you're seeing as a meteor. Sometimes we have meteor showers where we have a period of segments of these. So what is a meteorite? When a meteoroid does not burn up in the atmosphere, whether it's our atmosphere or another planets, and it actually hits the ground as an extraterrestrial rock that smashes into a planet or a moon, that is called a meteorite. So meteorites come in a variety of different forms, and they're all special. But I do want to take a few minutes to talk about the major groups and why they're important. There are three major classes or groups of meteorites, and then there's subclasses of each. But these groups are divided based on the majority of their chemical makeup. So there's stony meteorites like the chondrites we were just talking about. They are by far the most common on Earth, and 95% of every meteorite that falls on Earth is going to be one of these. It'll be classified as stony. Iron meteorites typically have the most intrinsic or monetary value because we can use the ores for purposes here on Earth. And they also kind of represent the beginnings of the Earth or the solar system, and they have a lot of the roots of old planets and the sun. Stony iron meteorites have a combination of both stony and iron, so they have about equal amounts of each. These are by far the most rare. So we're going to take a look at each type, and we'll start with iron because these are by far the most well-known. They are completely made up of metal like iron and nickel, and they represent the cores of asteroids or planets. And if you find them, this is one on Mars that the rovers recently discovered. And taking a close-up view, you can kind of see its composition here. This would be a very attractive find if you found it on planet Earth. Stony are the chondrites, and these are made of silicate minerals and other crustal materials. They are important because they make up, or likely made up, planets or large asteroids, but they've not changed since the beginning of the solar system. So they make up the goods that make up planets and large asteroids, but likely are just the stuff that didn't coalesce into these material or into these bodies. Most of these meteorites are fairly small in comparison to some of the others and represent the ingredients that were present in the solar system when the Earth initially formed. We, Earth, and the inner planets were likely made up of the same concentrations of materials that make up chondrites, the same chemical components. Now, what are stony irons? There are two major classes of these, and these meteorites contain approximately even amounts of silicate minerals and nickel-iron alloys. Pallasites are thought to form between the silicate mantles and the molten cores of a differentiated asteroid, and differentiation is a term we've talked about early in the semester where you get denser materials that sink to the bottom like iron and nickel of a planet or a moon, in this case an asteroid, and then the lighter elements come on top, they float up to the surface. Their primary silicate mineral that makes up the outer portions of them is olivine, and that's a mafic or an ultramafic mineral. In geology terms, that means that it is not like granite. Mesosideриtes are basically stony iron breccias. They have what we would call angular clasps that are stuck together with the makings of iron, nickel, meteorites, so there was a collision involved. We only have about 150 of them that have been properly identified and recognized on planet Earth. So if one of these were discovered, while they're not completely iron, nickel, they would be highly sought after. We can't talk about celestial bodies without visiting comets. And comets are the frozen remnants of the formation of the solar system. And we have a number of them that travel in our solar system, some that travel out and back in. And so comets are made of dust, rock, and ices, and they can range in just a few kilometers wide to tens of kilometers wide. As your comets get closer to a sun, they begin to heat up, which causes them to spew gases, and they can make this enormous glowing head referred to as a coma. And then the material that forms the tails is that basically ice tail material that's behind it. This can be millions of kilometers long. Comets are extremely fascinating. And as we think about comets, Halley's Comet is by far the most famous. It's referred to as actually IP Halley. That's its designation. It's famous because it marked the first time astronomers realized that a comet could visit our solar system more than once, that it didn't just come by, say hi, and never come back again. Instead, this comet has a cycle of 76 years where it makes a return visit to look at our skies, and we get to look at it for a while, and then it moves on. The last time it was here is in 1986, so if you're around in 2061, you should take a peek and wait for Halley's Comet to return back to our skies. Hale-Bopp comet is Comet C 1995-01, or otherwise referred to as the Great Comet of 1997. It's famous because this particular comet was visible in the Earth skies for over almost 2 years, but certainly over a year, 18 months. And I remember when it came and hung out, and you could go view it on a good night between 1996 and 1997. And it takes literally 2,534 years, so much longer to make its orbit around the sun one time as compared to Halley's Comet. So we don't know that much about it, and I hope you got to see it, but if you didn't, you'll just have to rely that it was a real thing and it did happen. Which brings me to space research, because all of this information that we've just learned in these 3 segments of astronomy could just be theoretical, but they're not. Some of it is. Some of our research is still theoretical. We don't know all the answers, which is why ongoing space exploration is needed. But so much is known. And one of the most important places that we learned a lot about deep space was right here in New Mexico with the VLA, referred to as the Very Large Array. Why is this so important? These are all radio telescopes. There are 28 antennas on site. At any one time, 27 of them could be operating because there's always a backup, but typically they may use a handful, and that makes a Y, and they're on a track so they can be moved around. It's really fascinating. And so these particular systems are much more effective than having, let's say, one radio telescope that's a mile wide. Instead, if we have a cluster, an array of them, we can get more radio waves from outer space than one single large dish telescope could have. And this allows scientists to amplify the radio waves from space, which enhances our ability to see the light from outer space. So I know that sounds like, okay, I thought it was radio waves, it's all you're hearing. We can transpose the radio waves and put a light frequency to them. It makes it very exciting in understanding how outer space looks. So the VLA, I've been there multiple times. It is an extraordinary place to visit. You can get a tour, and I would highly advise it. I've also been to this cool place called the Keck Observatory. This is in Mauna Kea in Hawaii, the Big Island. And while Mauna Loa is considered the granddaddy of all volcanoes, Mauna Kea is the highest place in the Hawaiian Islands. And I know because I've hiked to its summit, and it's really high up there. In fact, it's full of ice and snow on at the summits, especially in the winter months. What's really cool about this is it has twin systems at the top of it. And this is a strategically important place to put a telescope of these natures that have mirrors, because there's nothing obstructing the night sky. Not only is it the highest thing, there's no night pollution. So it is a really cool place to work and to visit. The mirrors are 10 meters in diameter and each have 36 hexagonal segments that work together to make a single piece of reflective glass to look into outer space. The Keck Observatory is an exceptional visit if you make it to the main or the Big Island of Hawaii. The Mars exploration program is another thing that helped us grow in our science knowledge and will continue to, I might add. What we learn on Mars may very well be the next frontier of outer space. The goal of this program is to explore our neighboring planet where we think we might be able to colonize with certainly robots, but humans as well. We already have a couple of robotic features there and doing their thing. And the knowledge we're gaining from the Mars program allows for this intense scientific data collection and discovery using robotic orbiters, landers, mobile laboratories in the future, much like the Mars Desert Research Station I was talking about. Here's one of the rovers right here. And we're learning so incredibly much from what what we've already done on Mars. And that's not even just, we're barely touching the surface of what's planned for the Mars exploration program at this time. So the Hubble telescope was the biggest, baddest one ever put into space when it was initially put out there. It doesn't get that title anymore. The Hubble's in our orbit, meaning planet Earth's orbit. That's an important characteristic to it, also a limiting factor. We launched it in 1990, NASA did, and it helped scientists determine a number of things. First, the atmospheric composition of other planets. What was out there in the Kuiper Belt, the Oort cloud, instrumental in identifying for the very first time that there was something called dark energy in the universe. You learned that in the first installment of our astronomy lessons. We are still taking pictures with it. It should last to probably somewhere between 2030 and 2040, but I want to compare something where we have a lot more clarity between Hubble and the next telescope. If you look at the bottom images here, same system. So visible light that we can get with Hubble, and when we refine it with the infrared capabilities of what we have with the Webb telescope, which you're fixing to learn about, we can do remarkable things. The James Webb Telescope is often just referred to as the Webb Telescope, but it is a very important new addition to how we can capture the cosmos and look into deep space. In fact, in 2021, it was launched and it was a game changer. While the Hubble telescope is truly awesome, Webb takes it to a whole nother order of magnitude of awesomeness because we can see further into space. We can see richer infrared views of places that we looked at with Hubble and beyond. We can see light that is 13.5 billion years old. That is just mind-blowing. So further than anything Hubble was able to see. And that means we can see the first stars and galaxies from when the universe was first made. That is just mind-blowing. It's like, this one's bigger than the Hubble. And together they have changed our knowledge and frontier and kind of reignited the need to get further into space so we can learn more about the frontier of outer space. That brings me to the future of NASA's space exploration program. The sky's the limit. What a cheesy thing to say, right? When we're talking about outer space, but that's really what's planned. So literally there are hundreds of missions planned for the next 10, 20, 30, 40 years of NASA's future. And what's planning on happening is let's send robotic probes to a number of these places in our solar system that we've not been or landed on, go back to the moon, go to Mars, maybe even colonize Mars, go to Jupiter's moons and outer planets, maybe the Kuiper Belt, see what's going on up there, and actually learn about exoplanets, which are planets outside of our solar system. To date, there's literally over 5,570, and there are more being recognized and classified regularly. So that number will just continue to grow. But exoplanets, big deal, because some of those could be a Goldilocks planet in another solar system, another galaxy. That's how all of the things that we have technologically are allowing us to grow. We are leaping forward in our knowledge of the incredible cosmos that we are just a small sliver of. So how does it apply to you in your everyday life? Images like this are not make-believe anymore. They come from something like the Hubble and Webb telescopes. We're only going to learn more as science reveals these remarkable secrets that, while we've looked at the outer night sky for as long as humans have been alive, we can see more than we've ever been able to see, and that's only going to improve with technology. This applies to you for a number of reasons. I'll keep revisiting that Cretaceous age asteroid that smashed into Earth at the end of the dinosaur time frame, which was the end of non-avian dinosaurs, at least a contributing factor. I've been to a place called the KPG boundary, where there is a iridium layer, which is a very rare earth element, very common in meteoroids. And that is thought to be from the asteroid that smashed in about 65, 66 million years ago into Yucatan Peninsula of Mexico. That was a mass extinction level event. What we're learning with astronomy can help prevent these kinds of things from occurring and wiping out life as we know it for humans. Also, they might be able to find other locations suitable for human colonization. They also may find new elements that we could use on planet Earth by harvesting them from outer space. There's so much that we just don't know. And so much that we do because of this advancement. There's so many great careers that you could look into doing. So if this is something that just makes you have joy in your life, where you're like, I love astronomy, well, maybe you should look at it as a potential career path, because there's lots of dimensions to it. There's astrobiology, astrophysics, there's astrogeologists, there's planetary scientists, there's moon scientists, there's comet scientists, you name it. There's all kinds of scientists. So there's a lot that you can do. And I have students who have been at this institution who are now working as astronomers. I actually have one in NASA. I have one working for other space programs. They didn't start off that way. They didn't know they wanted to get into this. It was once they started, kind of had a taste of geology and earth science and got into their next level of courses in their next institution, that they found something that hit the spot. So just know it could be something applicable to you. This information, of course, will be on your major exam, so make sure that you kind of pull out the key pieces and take a look at the due date and time in your instructor plan for that exam. Thanks so much and have a great day. Bye.